Hello friends, welcome to Abaqus equipment for quick and sound learning. In this video tutorial, I will take you through the continuous beam example which is subjected to complex loading such as varying distributed load and uniform distributed load followed by the two roller supports and then a point load. The other one end is fixed conditions. With this complex loading, we'll solve this or build this FE model in Abaqus CAE and then solve for the shear force and the bending moment diagram. So in the end we should be able to generate the results for shear force and bending moment diagram. And let me show you the overall animation, that is a deformation for the loading what I just shown for this continuous beam. Now let's go back and see the shear force diagram how it looks like. So we will generate these results through the tutorial build-up or FE model build-up, and this is the shear force diagram, and this is the point where you can clearly see where the shear force is 0. There is a bending moment at that maximum point. So again there is another there is a 0 point shear force. Okay, so let's start building this model, and this is the dimensions we'll be using. This is the unit system is in Newton, so I'll make this correction. So this is in Newton second meter, so no need, there is no ton. Let's not get into confusion. So we'll be using Newton and meter unit. Okay, so just look at the dimensions. So the span ranges around 8 meter with these splits like 0.5 meter and then followed by the uniformly varying load for 2 meter and then 2 meter of UDL and the point load somewhere in between these two roller support. So let's start building this model in Abaqus CA 12.1. Okay, so I start with the blank canvas. Okay, right, so I will start with the part. So I will say beam span. Let's say go to 2D planar, wire. So it is around 8 meters span, so somewhere around 20 meters should be size. Okay, so this is the grid and I will start generating these points. So I start with the 0.0. Okay, so this is the first point and then followed by 0.5 meter, 2.5, 3.5, 5.5, 6, 7 and 8. Okay, this is done, and we'll make a line segment for these points. This is done, and now we'll go to the property, and here we define, this is a normal steps for any of this static simulation. So defining the steel properties, that is we are using is Newton meter, so I'll be keying in 2.1 e raised to 11, 2.1, 0.28 Poisson's ratio. That's it. Then go to section. Here we need to select the beam, say beam, and then here the profile. So this is one of the important steps for this tutorial. So I'm choosing the I section, and I know the dimensions, so or you can simply refer these are the dimension I am going to give an input. So I have I, that is a 0.17, 0.34, 0.16. So thickness is 14 millimeter, that is 0.014. So I just copy and paste these numbers. Okay, so we have this number, just say okay, just assign this property all these elements. say okay, this is done, dismiss. And okay, this is the important step. So assigning the beam orientation. So guys, here I would like to grab your attention. So let me take you the picture. Okay, this is a typical beam element, and the T is your longitudinal axis, that is a tangent to the element axis, and then we need to define this n1 direction. So that is a direction which normal to the motion where the beam motion occurs. So here in this, if it is deforming in this plane, and obviously the normal has to be perpendicular to that plane. So there are two ways to define the normal for a given beam element. One is to define through the coordinates. So here the g coordinates is -1. Okay, so that is n1 direction. So this is n1 direction, and then, or you can choose a node, okay, which is lying in a perpendicular plane. So that is another way of defining the n1 direction. So we'll be, for this tutorial, we're using the coordinate way of defining the beam normal. So let's go back to the tutorial build up in CAE, Abaqus CAE. Here it is. Okay, so I'm going to select all these elements, say done. In general, or by default number, you see these numbers, that is -1. You have to make sure that the g coordinates is -1.0. So just say enter, that's it. So you will see those numbers or coordinates over here. So this is the n1 direction, and now we will have, so let's see the how the beam looks like. So go to this part display option and render this beam profile. Say okay. Okay, so here it is. So you can see how the beam profile looks like. This is the I section what we chose. Alright, so moving on, we'll go to the assembly part. Just say beam span, okay, and then go to the mesh. Okay, so, or you can say go to the step. So you have to define the static step. So this is a very usual general process. Say just okay, that's it, and move on to the mesh part. So in mesh, so here I will go element types. So, okay, before that we need to make this independent. Alright, so go to assembly, and in assembly we need to look for this part, this instance, and just make it as independent. Alright, so now go to mesh. So here element type, okay, select all these elements or all these line segments, say done. We are using the standard and linear. So, and then the beam element, that family, just say okay, done. And here we'll be choosing the size 0.5 meter as the element size. Just say apply, okay, mesh it. Alright, so I'm just displaying the node IDs over here, or say element IDs. Okay, so we have in all 16 elements. Okay, and now let's move to the loads and boundary condition part. Okay, so just to understand the boundary conditions and loading, so we have one end, that is this edge is fixed edge, and then there are two nodes which are roller support. I'll create the node set for each of these nodes or boundary condition, and then we move on to other loading. So let's put a constraint first, or define a set for the constraints. For that you go to sets, say create, okay, node, I'll say this is fix, continue. So I'll be choosing this node, done. And I will again say the roller support, roller nodes, continue. So I'll choose this one, and then shift, somewhere here. Okay, yep, Let me see the dimension again. Yeah, we have 2 meter, we have another support. Alright, so this is correct. So this is done. And then I have varying load element set. Okay, so I just creating these things. Those are the 4 elements. Over these 4 elements we need to define the varying distributed load. So I'm just creating the element set, and later on I will explain how to define the actual loads in over these elements. Just pay attention how I defining this set. Okay, and then I'll have another set for UDL elements. So that is another 4 elements, 8 to 11. Okay, so this is all depends upon the how the span is split for the loading. Done. Okay, and we have a node for the concentrated load. Okay, that is point load node. Continue. So we'll have, okay, so this is the node what we're choosing. Done. Okay, now move on to the BC part. Create, say fix BC. Continue. So we have set defined, that is fix. Continue, and we have to choose all 3 degrees of freedom. We have to constrain. Okay, this is done. So you can see the symbol is highlighted, and now I need to create another one. So this is roller BC. Continue, and here it is roller nodes. I'm selecting as a set. Continue, and I'm supporting only, the constraining only the U2 part, that is vertical direction. I am, as this is a roller support. So you can see these 2 symbols appeared. And now moving on to the loading part. So we will start with the varying distributed load. So this is a slightly critical part of this tutorial, how to apply the varying distributed load. For that you go to create load and then say vary, put some name, varying load, so line load. Okay, in this types of selector step you need to choose the line load, mechanical line load. Continue, and here I am choosing the element set for the varying load. Continue, and here this is the crucial points. So you have to choose in distribution user defined and fx. Okay, and that is analytical field equation we need to define, as this is okay. So for that we need to do some prior preparation. So guys, if you see the how the load has been distributed and the magnitude part, so it is 4000 Newton per meter, and it is uniformly varying, and after end of 2 meter it is 0. Okay, so the same thing. Okay, so I have used this information to plot this curve and then extract the equation. Okay, so once we know this equation of this curve, we can define that equation so that the Abaqus will automatically calculate the corresponding loads applied over this span. Okay, you can simply use the Excel sheet and plot this curve and extract this equation. In this case we are using only the linearly varying, or in more complex cases there could be the second order curves or some other more complex shapes you can use for as per your requirements. So as of now it's a linear equation. So this is the equation what we have, that is minus 4000 x plus 10,000. These numbers based on these inputs, that is 4000 Newton per meter and 0 Newton after 2 meter. Alright, so let's go back and key in that. So minus 4000 star x plus 10,000. So let me see that equation. Yep, minus 4,000 x plus 10,000. All right, minus 4,000 x plus 10,000. Okay, just okay. And here you have to select the analytical field. Let me bring it to center. Select as analytical field, and here it is define just minus 1.0. okay okay guys, so this is what you see on your screen. Okay, now let's define the UDL part. So this is the UDL. So stick to this line load, continue, and I'm choosing the UDL elements, continue, and here just leave it to uniform, distribution uniform, and component. So I have that minus 1200 is the magnitude of the UDL. So this is what it appears, and then now there's a point load. This is a point load, continue. So we have a set over here, and the magnitude is 1500 Newton. So it's in minus. Just say okay. That's it. Defined all the required loading and boundary condition for this continuous beam example. There is one more important trigger we need to make in this FE model. That is, we need to request the field output for the section force and bending moment for each of these elements. So for that, go to field output request, say create. Okay, continue, and here you look for the forces. Just scroll down, and we have to check in this box, nodal force in beam section orientation. So this is, unless we trigger this option, we won't get the output. So just say okay. Alright, so we'll create a job, and so I'll put some name, say tutorial 11, continue. Okay, just say submit. Okay, so the job is completed. We can see the status. Okay, so now let me load the results. This is the magnitude, that is the deformation, what it is showing. It is 0.919 millimeter. And now let's see the, you can also see the 1 mesh stresses. So all these things you can post process it. And now let's get into the important part to plotting this shear force and bending moment diagram. For that we need to create a path. Okay, go to tools. Okay, so first thing, you have to be in visualization mode, and tools, path, create, say node list. Alright, say continue, and click on add before. You have to select the nodes along the longitudinal length of the beam. Okay, I will show how to do it. So this is the first point, and just here is the second point, and the node will get highlighted automatically. So you have to just place the cursor okay. We have built this path, say done. Okay, so if you know the node labels, you can simply type in these node labels. So that is another way of creating this path. So just say okay, create XY data, and select the path, say continue, and here select the path 2. This is the one we have created just now. And in field output, you select the FOR SO2, that is the nodal forces in the beam. So that will give us a shear force diagram. Say OK and plot. So this is the shear force diagram what you see on your screen. So just to save our time, I have already taken this plot on this page. So let's plot the bending moment diagram. For that, again XY data, path, continue, and select the path 2 and field output. Here is the moment. Say OK and say plot. Okay. So this is the bending moment plot. I take this picture and I have just put these plots one below the other so that we can compare the profile of the shear force and the bending moment diagram. So if you see this, you can see the beam with different loadings. Like here it's a fixed condition. So due to this fixed condition, we'll see some bending moment over here. It start with some 6,500 Newton meter, and later there is a variation and due to this varying load, and this due to this varying load we expect the order of 2 curve. This is what we see, and here the shear force is 0 and then corresponding bending moment at its highest. And then so we see there is a UDL, and due to this UDL there is again a second order curve what we see, and then there is a roller over here, and there is some reaction force at this point, and then followed by the effect of the point load. So this is what we see once we plot the shear force and the bending moment diagram. From this diagram you can further design and evaluate how the beam section is behaving for these given loads. And let's do a small tricky exercise over here. So let's change the boundary condition from fixed to simply supported and see how the bending moment diagram changes. Okay, so let's do this tricky exercise quickly. So for that you go to the loads. Okay, and here I'm going to change the boundary condition from fixed to so only the simply supported part. I will submit this job again. Just to save time, I have the results with me. I simply loaded those results ODB file, and let's see now the shear force and the bending moment diagram. The process remains same. You go to XY data, path, and say field output, and here again the same process. Okay, plot. Alright, so this is the shear force diagram. So this is the already I have pasted over here. So this is what we got, and now we'll plot the bending moment diagram. The same process. Go to path and here select. So this is, so you can see due to change in the boundary condition, the bending moment, so we are changing from fixed conditions to the simply supported condition. The bending moment is become 0 at this edge. So that's what we wanted to show you and understand. So you can see again the shear force and the bending moment diagram due to change in the boundary condition from fixed to simply supported. It start with a bending moment 0, so it is not offering any resistance moment. Guys, this is what I wanted to demonstrate you through this video, how a continuous beam can be solved by subjected to different complex loading. Understand and try on your own with your own given loading conditions. If you like this video, please like us on YouTube and please subscribe us so that we can bring you new exciting videos, and also leave your comments. That will be helpful for other users as well. Thank you. Bye bye.